So we begin a whole new chapter, chapter 14, 14.1 on vector valued functions. Well, we kind of already defined these vector valued functions to describe a line in space, you know. But finally, we're going to get into other kinds of functions, no longer a line in space, no longer just what you call them. Um, yeah, just a line in space. Actually, we're going to talk about other curves, other settings, and other things that we're going to do with vector valued functions. Pretty much everything related to what a function is. Find the domain, find the limit of a function. So we're finally getting into the calculus, if you will. All right. And then we are going to graph a little bit of parameterized curves. Maybe not that much for now, but we're going to keep doing this along the way as we progress through the course. Okay, so we define a vector valued function back in 13.5 as either a function in R1 or in R2. That is, recall that a function relates input and output. But how does that work with vector valued functions? So there's two ways, or rather two cases. Number one, where we go from R to R2. That is from where the input is one single integer, it's one single value, not just an integer, and the output it's actually a vector in two dimensions. You know, that's when we use vectors in the plane. And then the second case, when we go from R to R3. That is a vector where our input, in this case t, outputs a vector in space in 3 dimensions. So that's the formal notation we use to describe this relation, this input-output relation. All right, so let's talk about the limit of a vector valued function. So here's where all our Calc 1 and Calc 2 techniques to finding limits will come back. L'Hopital's rule, everything you can think of, right? So here, the thing when it comes to finding the limit of a vector valued function, so what we do essentially is find the limit of each individual component on the side, and then the result will be a vector. Okay, so the thing here is, if the limit for one of the components does not exist, well, then the limit for the entire vector valued function is not going to exist. So the minute one fails to exist, it messes all of it. Okay. All right. So given r of t equals c over t plus 1 in the direction of I plus 5e to the negative t in the direction of j, they're asking us to find the limit as t approaches infinity. Well, so number one. So for letter A, let's do these limits on the side. And by the way, be sure to use the proper notation. That is, put the limit symbol and where it's approaching to. If you just put the the expression, then you're just evaluating an expression. You're not finding the limits, and those are two different things. Notation matters here, okay? So t approaches infinity, t over t plus 1. Okay, so I mean infinity over infinity plus 1, that's the indeterminate form, infinity over infinity, right? That means we can do something about this expression to find the limit. And there's a couple of ways to evaluate this limit. One, the old-fashioned way is to divide all the terms in the expression by the highest power of the variable in the denominator. Or if you learn the L'Hopital's rule, which you know by now, use L'Hopital's rule. So that's going to give us the derivative of the numerator, which is 1 over 1 plus 0, which is simply 1. Okay. So we are computing the limit of 1 as t approaches infinity. This is simply going to be 1. All right. Another way to find this limit without doing L'Hopital's rule, if you will, it's by considering the fact that both numerator and denominator are polynomials. And when we have polynomial over polynomial, we just go with the ratio of the leading coefficients if the degrees of both polynomials match, which in this case it is the case. All right. Okay, so that's part A. Let's do part B. That's the limit t approaches infinity 5e to the negative t. Okay. So by direct substitution, so to speak, well, so we substitute infinity right here. Where is e to the negative t going to go? Negative infinity. Okay. 0, right? 0. That's because, well, let me actually substitute it. So a better way to write this, t approaches infinity, rewrite this as 5e to the t. Well, the denominator is going to get really big, right? What do we get when we divide by really big? 0. I mean infinity. I mean, well, but divide by infinity, we get 0, right? Well, these are the results of the individual limit here. Let's go back and say this is equal to, we need to express these results as vectors, 1 and 0. Okay. Another example, a very simple example as well. So, for letter A, well, that's actually a vector in 3 dimensions, a vector in space. Okay, so number 1, limit as t approaches 1 of the square root of t. What's the square root of 1? By direct substitution, this is the square root of 1, which is 1. Very simple limit here. Letter B, limit of ln of t over t squared minus 1 as t approaches 1. Okay, so what's ln of t in the numerator? 0. What's 1 squared minus 1? Isn't that another 0? So we get the indeterminate form 0 over 0. That means we will, we're good to go and do some algebra, maybe some factoring, maybe some rationalizing of a radical, maybe some, what else? Maybe simplifying a complex fraction, but that's none of the 3 cases because we have functions other than radicals and polynomials. So L'Hopital's rule, right? We need to indicate that we're using L'Hopital's rule somehow. Keep writing the limit notation. The derivative of ln of t, that's 1 over t. The derivative of t squared minus 1, that's 2t. Let's simplify this because it's going to be better to simplify this one. Okay, so that's essentially limit t approaches 1 over t times 1 over 2t. That is limit t approaches 1 of 1 over 2 t squared, which is, by direct substitution, now let me continue here. Actually, yeah, I need a space. Oops. So that'll be 1 over 2 times 1 squared. That equals 1/2. So 2 out of the 3 components. All right. The third component, the limit for the third component, let me call that a c. That equals the limit arc cosine of t as t approaches 1. Well, in this case, arc cosine of 1. In this case, what angle gives us a cosine equal to 1? That's the question. What is it? 0. So the 3 limits together, write it as a vector. 1, 1/2, and 0. Of course, these are very simple limit exercises, but of course, you may get something more elaborate, like the ones you got in Calc 2 or in Calc 1, where you had to use the other different indeterminate forms, or limits where you have to explain a little bit with a graph that may not work by using the L'Hopitals or by direct substitution. So there's a bunch of cases, right? Okay, of course we care about the domain of a vector valued function. And here is where you will test yourself how much do you know about domains of a function. All right? And here I have what I could gather, like the most complete, I guess, guidelines to find the domain. Every single fact, restriction, call it whatever you want, to find domain of all kinds of functions that you may have used. Okay, so there are some functions, of course, that do not have restrictions. You see that function, all real numbers, all real number. You don't have to do any algebra to find out what the domain is. That is the case of polynomials. Radical functions with an odd index, like the cube root, the fifth root, the seventh root, etc. What else? Exponential functions, unless your exponent has a rational function in terms of the variable and has an undefined value, but in general, e to the x, e to the negative x, e to the x cubed, those kinds of exponential functions, even exponential functions where the base is not necessarily the base e. Okay. What else? Trigonometric functions such as sine and cosine. Recall that the remaining trig functions, tangent, cotangent, secant, and cosecant, have vertical asymptotes. Those are values of x where the functions are not defined. Okay. What else? Inverse trigonometric functions such as the arctangent and the arccotangent functions. Those are functions whose domains are all real numbers. Hyperbolic functions such as sinh, costant, and sich. Okay. Inverse hyperbolic sine, that is sinh inverse of x. Okay. Now, what about the restricted function? So again, every time you see a radical function with an even index, like the square root, the fourth root, the sixth root, the 28th root, even indices, what do? You set the radicand greater than or equal to 0 and solve the inequality for that given variable. Okay. The next function with restricted domain is the logarithmic function, and it doesn't matter the base of the logarithmic function. Okay, that doesn't matter. It could be the logarithm base e, which is the ln, logarithm base 7, logarithm base 10, your favorite. Doesn't matter. It's the process to find the domain for that function is similar to that of the radical of even index, except that we set what we call the argument, not the radicand. The radicand is the expression inside of the radical. The argument is the expression inside the absolute value function. We set it greater than 0 only, not greater than or equal. Okay, and solve the inequality for the given variable. When we have a rational function that is strictly polynomial over polynomial, the red flags for these functions are the values that make the denominator equal to 0. That is, we set then the denominator equal to 0 and solve that equation for the given variable. Those answers we get for that equation will be the restricted values. All right? Okay. Find the domain of inverse functions such as arcsine and arccosine. Well, we will bound, so this might be new for you. We don't set it greater than, less than, no. We bound the argument, that is the expression inside the arcsine and arccosine. We bound it between, bound the argument between -1 and 1. Why do we bound between -1 and 1? Because again, where does the arcsine come from? That comes from the sine function, whose range is -1 to 1, right? That's the inverse function. When we define an inverse function, we interchange the domain and the range. So the range of the original function now becomes the domain of its inverse function. Yes?
So is that like squeeze theorem?
In a way, it's the squeeze theorem. However, the squeeze theorem is to limit. I mean, the limit of an ugly-looking function that we can evaluate somehow by means of finding side limits, and yeah, we create that sandwich or that squeeze, right? So, but yeah, I guess because of the inequality that resembles like the squeeze theorem, but it's not necessarily squeeze theorem, all right? So. And we set it between -1 and 1. That's because that's the domain of the inverse sine and cosine, which is the range of their corresponding function they're coming from. To find the domain of the inverse functions arcsecant and arccosine, well, we need to solve this absolute value inequality. So we set the absolute value of the argument, that is, are you greater than or equal to 1? That means, well, back to your intermediate algebra, the way we solve this absolute value inequalities, this is equivalent to solve u less than or equal to -1 or u greater than 1. All right, so that's going to take us back to our algebra days here. All right, let's have a look at some exercises, quite a few actually. Okay, find the domain of each vector valued function and express your answer using interval notation. Okay, so r of t equals the square root of 5t minus 3 and square root of 6 minus 2t. Okay, so let's find the domain of the two functions separately. All right, so number one, I'm going to set this 5t minus 3 and square root of 6 minus 2t. And I'm going to find the domain of these two functions. Well, notice in this case, I'm taking the time to find such domains because, well, these are functions with restrictions, okay? So, otherwise, if there were polynomials or radical functions of an odd index, I would just say all real numbers and flip the page. But it's not the case. Okay, so for radical function of an even index, set the radicand, that is 5t minus 3, greater than or equal to 0. The reason why we set it greater than or equal to 0, that's our formal way to exclude the negative numbers, because you can't take the square root of a negative number. Well, yes, you can, but that's going to give you imaginary numbers, which give rise to complex numbers, which is a whole nother class. Functions of complex analysis or complex variables, that's a whole nother field. And we care about functions of real variable here. Okay? So, let's solve the inequality 5t greater than or equal to 3. T greater than or equal to 3/5. Okay? All right. Let's solve 6 minus 2t greater than or equal to 0. That means negative 2t greater than or equal to negative 6. And divide both sides by negative 2. That's 2 greater than or equal to 3. Agree? Huh? The sign flips. Remember, let's recall that every time we multiply or divide both sides of an inequality by a negative number, the inequality symbol reverses, right? So what's the reasoning behind? For instance, okay, do you guys agree that 3 is less than or equal to 7? Okay? But what if I write the sentence negative 3 less than or equal, if I change the signs? I would need to flip the inequality symbol to turn it into a logical sentence. Negative 3 is greater than negative 7. Okay? So, now what are we going to do with these two results? So number one, let's graph these sets. Let me call this set A and set B. So set A, so let me label the 0, if you will, to have a good number sense. You don't have to mark the lines, especially because in many cases we may have fractions, you know. So just make sure that we have a good number sense here. So I'm going to go to 3/5, which is roughly here. This is where 3/5 is. Now, in accordance with the inequality symbol, am I going to shade to the right or to the left? To the right. Okay, I'm going to put brackets because brackets are related to greater than or equal or less than or equal, depending on the case. And I'm going to shade to the right. All right, let's have a look at the next set. T less than or equal to 3. So 3 is roughly here. Okay, so this is 3/5. 3 is here. Am I going to shade to the right or to the left of 3? To the left, okay? So I'm going to use a different color for this. and I'm going to shade to the left. All right, how are we going to find the domain of the vector valued function? We're going to find the intersection of these two sets. In other words, the overlap. So I'm going to draw a third line right here. A third line, a third number line to represent those overlaps. Let me label this properly: A intersection with B. Okay. So essentially I'm going to repeat these shadings here. So that'll be 3/5 and 3. So to the right of 3 with this color, and to the left, to the right of 3/5 and to the left of 3. Now, well, for some reason, maybe I should have chosen different colors. In this case, the domain of the vector valued function will be where the green color and the pink color kind of blend. That is, between 3/5 and 3. So the domain using interval notation for this, that is 3/5, 3. All right? So that's our domain of the function. All right. All right, let's have a look at another case. So the next example, it's another example with a vector valued function in R2. It's going to get more interesting when we get to 3 components at the same time, all right? So, what do we have here? We have a logarithm along with a radical with a polynomial. Oh, geez, okay. This one is going to be fun. All right. Logarithmic function. So, again, coming back, referring to the guidelines in the previous page, well, we set the argument of the logarithmic function greater than 0, not greater than or equal, just greater than. Okay, so that means we're going to set 6 minus 2t greater than 0 and solve the inequality for the variable t. That is, subtract 6 on both sides and divide both sides by 2. That changes or reverses the inequality symbol, t less than 3. So we're done with the first domain. So the first component is restricted to values that are less than 3, not equal to 3. All right? That means 2.5, 2.9, 2.99999, infinitely many 9s, and then every one, but not quite 3. All right, what about the second component? Any ideas for the second component? Yes. Yeah, you.
Everything like in the radical is greater than or equal to 0.
And that's because this is a radical of an even index, right? It's a square root. If we had a cube root, then all real numbers, but that's not the case. So let's set it up. Okay, so let's set. Oh, let me label this as A, by the way. Our set A. So B. Let's set t squared plus 2t minus 8 greater than or equal to 0. All right? So we need to solve this polynomial inequality. So this is not just as easy as moving things around like we did in the previous set for A. So we need to go back to how to solve polynomial inequalities. Well, so let me highlight the part that matters. Well, maybe not now. Maybe later. Okay. Well, to solve polynomial inequalities, let's forget about the inequality for now and turn this into an equation. T squared plus 2t minus 8, set it equal to 0, and solve the equation to find the values of t. We're going to talk about those values. All right, how do we factor this trinomial? Any ideas? I call this the double bubble method. Whenever we have a trinomial whose coefficient is 1, just use the double bubble method. So here we have the bubbles here, right? Put the variable t and t Find factors of negative 8 that add up to 2. What are those numbers? 4 and negative 2. So plus 4, negative 2. Set it equal to 0. And using the zero product property here, this means t plus 4 equals to 0 and t minus 2 equals to 0, which means t equals to negative 4 and t equals to 2. Okay? What are these numbers? This is what we call the critical numbers. It doesn't have anything to do with finding max and mins, like in Calc 1. Well, yes, in a way. You use those critical numbers in Calc 1 to analyze the behavior of the function. That is, those are the values where the graph changes from increasing to decreasing or vice versa here. But that was for the derivative of the function. For the original function, these critical values indicate the values of x where the function becomes or goes from positive to negative or from negative to positive. And well, positive, negative, negative, positive, that's going to help us solve this inequality here, okay? Now, yes, of course, I mean, you want to plug in infinitely many values until you get true statements and a bunch of false statements, but let me show you a way to solve this problem. Well, I'm going to draw a number line. Okay, I'm going to draw a number line. And I'm going to plot these two numbers on that number line in order. Okay, negative 4 and 2. So that gives rise 3 intervals to test. Okay, so yes, we're going to choose values, but I mean this number line approach is going to be more visual to help us get the actual values. Okay, so and these factors I got from the factoring, the t plus 4 and the t minus 2. I'm going to put them next to the number line. T plus 4, t minus 2. Okay, we're going to choose test values. Your favorite test value. Keep it easy, keep it simple. In this interval, another test value. In this interval, another test value in this interval. Okay, what is a good number between negative infinity and negative 4? Not negative 4. Excluding negative 5. Okay, so that's our test value, negative 5. What is a good test value between negative 4 and 2? 0. Okay. What about between 2 and infinity? 3. Okay. You could do 7 million or whatever, but it's going to work. Keep it simple. Okay. What are we going to do with these numbers, with these test values? Okay. I'm going to evaluate this negative 5 on these two expressions. Okay. Negative 5 plus 4, what is that equal to? I don't care about the number. All I care is the sign. It's negative. Okay? Negative 5 minus 2. Positive or negative? Negative. Okay, let's go to the second column. 0 plus 4. Positive. 0 minus 2. Isn't that negative? Okay, 3. 3 plus 4. Positive. 3 minus 2. Also positive. Alright? Now, this is what we're going to do. We're going to multiply each column of signs. Okay, so this will be negative times a negative. What is that? Positive. Positive times a negative. Positive times a positive. We're good to go back to the inequality. Hey, they're asking us for greater than or equal to 0. What does that sound like? Positive or negative? Okay, so we're going to shade the positive intervals here. That is, this interval right here and that interval. And let me be clear about, oops. It's going to go in this direction and that direction. All right, so we have the problem pretty much solved right here. Okay, so let's go and now let's put all of it together. Set A. So for set A, for set B, okay, let's put the 0 in the very middle for reference. Okay, let's shade set A. Okay, set A is all the numbers less than 3, excluding the 3. So that means I'm going to go to the number 3, okay, But in this case, I'm going to shade to the left because of the inequality symbol, and also I'm going to use parentheses. Alternative, you could use an open circle. That's another way. You could use the one that works best for you. All right, then, okay, let me shade. Oops, no, not this one. And let's go about the next one. Okay, I'm gonna go back to -4. Oops. And 2. That means, let me use blue again. Oops. These two sets. All right. So, we need to find the intersection, the overlap of these two sets. That is, okay, let me do this, let me do that, let me do that. With blue 4 to the right of, what is that, 2, and less than 4, right? So, okay, that's -4, 2, and 3. And for 3, that's going to be to the left of 3. Okay? I think these colors are a little better for the overlaps. Okay, so we need to look at the overlaps. So where the colors blend are in the interval -infinity to -4. Here we just have the pink. Here we have the two colors blending from 2 to 3. And here we just have blue. So we just need to state the intervals where the two sets overlap. That is, domain, we're done with this one. Domain, -infinity to -4, bracket, union symbol, 2 to 3, including the 2, excluding the 3. All right? So that's the domain for this vector valued function. All right. Let's have a look at the next example, the third one, third example. Okay, let's put all inverse trig functions now. Arcsine, arccosecant, and arctan. Okay, so let's see. So inverse trig functions like the inverse sine, well, we need to bound the argument between -1 and 1 and solve the compound inequality. Okay, so that means we need to set t minus 3 between -1 and 1, including the endpoints, because the function is defined at those values. Okay, so when we have these kinds of three-side inequalities, that is a compound inequality, our goal is to leave our variable in the very middle. So all we need in this case is to add 3 to both sides. That is 3 minus 1, that equals to 2, and 3 plus 1, that equals to 4. So we're done with the first set. Let's call that set, let's call that A. All right. For second set, set B. How are we going to go about set B? Okay, let me make more space in here. All right. So in this case, we need to, okay, let me go back to the arc cosecant. What is that? Arc cosecant, right? So for arcsecant and arc cosecant, we need to set two inequalities. So that is the argument less than or equal -1, or the argument greater than or equal +1, and then find the union of both of those, and then the intersection for the overall domain. Okay, so let's set so the inequality, first of all, or the absolute value inequality, that is absolute value of 1/3 t minus 2, set it greater than or equal to 1. That means this implies solving 1/3 t minus 2 less than or equal to 1, or 1/3 t minus 2 greater than or equal to 1. Oh, this is less than or equal -1, by the way. Right? and the other one greater than or equal to 1. And let's solve each individual inequality here. All right, add to the both sides. That's 1/3 t equals to 2 minus 1, that equals to 1. And here, less than or equal, and t less than or equal to 3. For the second inequality, add 2 again. That equals 1/3 t greater than or equal to plus 1 equals to 3. Multiply both sides by 3. T is greater than or equal 9. All right? I'm not going to draw these sets separately. I'm just going to go and put them together. Now, let's call that B. Set B. Okay, what about the third component, the arctangent function? What's the domain of the arctant function? I think that is the range. All real numbers, so no need to represent anything. Whenever you have one of the components being all real numbers, just say t belongs to all real numbers, and well, you don't have to, well, that basically represents the entire number line shaded, but you don't need to do that. In the end, you just care about whatever has restrictions. Okay, let's put all this together. So, set A. Set A, have the 0 here. Set B, have the 0 there as well. And using some number sense, let's plot the numbers. So, okay. So the set A means between 2 and 4. That is 1, 2, and 4, like this, all right? And let me shade that with a different color. Let me shade that with, let me use blue. And the second set, oh, careful, because this is comprised by two inequalities. Number one, t less than or equal to 3. That means, let me go to the number 3. Actually, let me make this a little smaller, so I'm going to need more space. So 3 is roughly here in the between 2 and 4. Less than that, let me go about shading it with red. And okay, so that's 3. And greater than or equal to 9. So 9 will be roughly 9 and on. All right. Okay. Oops. This looks weird. Okay. Now we're going to overlap these two sets. Let's overlap the sets. That is A and B. So that is blue here and red the other way for the other sets. Where do the colors overlap? Do you guys notice it's only one interval where the colors overlap? Or I mean where the colors blend? That is where the two sets overlap. And that's only between 2 and 3. Right? So domain that's simply between 2 and 3 inclusive. Okay? All right, what about number 4? Let's have a look at this monster here. All right? Okay. Yeah, don't let it scare you. I know it looks ugly, but you'll see. You're going to like this one. All right? Okay. So, quotients, radicals, logs, twigs. We have a bunch of stuff going on. Okay. Let's see. The arctan function. So this is A, B, C, if you want to label, D, E, and F. All right? All right. So, what about A? Arc10T. What's the domain of Arc10T? All real numbers. So for T, all real numbers. Fine. Letter B. E to the T squared. Do you see any restrictions to this guy? If so, what would be the restrictions? What was that again? All real numbers, right? I mean, unless you had a t in the, unless it looked like this, e to the 1 over t squared, then it would be undefined for t equals to 0, but it's not the case, right? So another all real numbers. Letter C. Okay, ln of t squared plus 5. What do we do with ln's? Don't we set the argument t squared plus 5 greater than 0? Solve the inequality, all right? Okay, let me try solve this inequality. Okay, let me move that 5 to the right hand side. That means t squared greater than negative 5. Okay, think of this statement. T squared greater than 5. So, what number squared is greater than negative 5? All real numbers, because any number squared is going to be positive, and every positive number is for sure greater than a negative number, right? Yes. So that means T all real numbers, okay? Let's keep going. Okay, 90 squared plus 49. Okay, I'm setting this 90 squared plus 49 equals to 0 because that's a polynomial in the denominator. So there's potential red flags. That is numbers that make the denominator equal to 0. Let's solve this quadratic equation, an inequality equation. 9t squared plus 14 equals negative 49. T squared equals negative 49 over 9. So t equals plus or minus the square root of this number 49 over 9. Hold on. Square root of negative 49 over 9. What is that equal to? Yes. It's an imaginary number, but do we care about imaginary numbers? No, so that means there's no restrictions. If the solution to the equation is not a real number, it's an imaginary number, so no restrictions. Substitute 1, substitute 2, even for 0, 0 plus 0 squared, Okay, that's fine. Okay. That's D. Let's do, okay, so that's D, that's E. Well, number 1, we have a radical of odd index in the denominator. So we may think of, yes, all real numbers, right? However, we still have variables in the denominator that could potentially be 0. Well, let's have a look at that. So we need to set 25t squared plus 64. Okay, underneath the radical. Cube both sides. 25t plus 64 equals to 0 squared. 25t squared equals to negative 64. Same situation as before, right? Negative 64 over 25. So when you're solving an equation like this, you don't even have to go through the square root property. Here is where it gets a little crazy because what number squared equals a negative number? So the equation has no real solution. That means there's no restriction. So another all real numbers. All right. Lastly, for F. So for F, what are we going to have? Number 1, sine t plus 5 equals to 0. So there could be potentially periodic values, maybe infinitely many values of periodic form because it's a trig function. So we set the denominator equal to 0, that is sine t plus 5 equals to 0. Let's solve the trigonometric equation for t. Sine t equals to negative 5. What did you think about this equation? Hmm? What are the solutions to that equation? Hmm? Infinitely many solutions, perhaps? No solution? Why is that a no solution?
Because the range of sine t is only -1 to 1.
-1 to 1. So another way, a graphic approach, if you will. So essentially, when solving this equation, you're finding the intersection between the sine function, which goes, by the way, between -1 and 1, and the horizontal line y equals to -1, -2, -3, -4, -5. Are these two graphs intersecting at all? No solution. That means this is good for t for all real numbers. So what is the intersection of all real numbers, all real numbers, all real numbers 6 times? All real numbers. So domain, using interval notation, all negative infinity to positive infinity, or in set builder notation, x such that x is all real numbers. All right? So that's about finding the domain. So, and again, see how we pretty much put together all techniques in all these problems, this is hopefully a good review for you to find domain of a function. We're going to come back to finding the domain of a function when we get to functions of 2 variables and 3 variables. So not just 1 variable, so it's gonna get fun because actually, so in this case we're describing the domain of a function as an interval of values. Now when it comes to finding a domain of a function of multiple variables, it's not just going to be an interval of values, it's actually going to be regions, planar regions, or maybe solid surfaces, or solid regions, if you will, which will be the basis, no pun intended with the basis, to describe the solid base of a solid, to find its volume then by using the double of a triple integral. So you will see how everything we will be doing here will connect. You'll see. All right, let's see what's next. Okay, curves in space. So again, let's just review the general form of a curve in space. So we call positive orientation, which is the direction in which the curve is generated as the parameter increases. T equals 0, 1, 3, 4, 5, not backwards. I mean, of course, we can somehow work backwards, but those are specific cases, The thing here is, how do we graph these functions? Well, this is not something I'm going to ask you to graph by hand because it's not a feasible task. So I'm going to use again GeoGebra to do this. Okay. So number 1. Okay, orientation. For instance, if you have some curve that looks like this, the curve may be oriented in this direction. And when it comes to circular curves, typically positive orientation means counterclockwise. Remember how connecting the idea of trigonometric functions with points on the unit circle or a circle of any radii, and well, the angles increase counterclockwise. So, in general, we will indicate the orientation with these arrows right here. Then you're going to go in a counterclockwise direction. Well, if we were to plot one of these curves in space, we would start by plotting the projection onto the xy plane and then make it 3D. But again, I'll show you in a second. I think, okay.